So I'm sharing with you the Canvas site right here, and made a decision. I actually made it last Friday of what do we do today and Wednesday, and I had two choices. One was adding of angular momentum, the angular momentum and actually the spin angular momentum of both a proton and an electron, and that's an interesting piece of mathematics. Kind of muddied a lot with some poor notation. It results in something called Kleps-Gordon coefficients, which allow you to calculate how the momentum and the spin angular momentum of a proton and an electron are combined. And while I thought that was important, um, wish we had more time this semester as always, but even more so with the loss of a week, I decided that the better answer was to at least get you an inkling into what do you do when the potential is complicated and can't be figured out analytically, and you need to invoke something called perturbation theory. And we're only going to talk about one piece of perturbation theory, but I think we're going to jump to chapter 7, one more tutorial. Okay, it's called non-degenerate perturbation, which might imply there is a degenerate perturbation, and you'd be correct on that. And we're not going to get to that. If you want to see that, shoot me an email. I got some more notes on that, and I have a tutorial on that. But we're not going to cover that this semester. And of course, everything we're talking about is time independent. There's also some time dependent perturbation theory, which we're not going to talk about. But this will get you the idea of what we're doing in it. We're jumping to chapter 7. You didn't know that before, so I have no expectation that anybody's done any reading. I will go through an example this morning to talk about how you start this up. What's that? Somebody talking to me right now? Or is that just background noise? Okay, nope. I don't see anybody raising a hand, and I don't hear anybody anymore. So anyway, perturbation theory will be what we'll spend today with, and a little bit of Wednesday, one more work, one more tutorial, one more worksheet, and I've got to do on the reading day with homework 8 as well. Is also due that day. Okay, I do still plan normal office hours today and Wednesday. If you have more questions, things you're getting ready for the take-home final, which should be posted next Sunday, that should be the last thing posted to Canvas. I think every assignment, every homework is posted right now. The only thing left is the exam, which will come out this weekend. If you have any need for office hours and the normal 3:30 time I've been doing on Monday, Wednesday doesn't work for you, let me know, because Friday's completely free on the reading day. I don't teach on Thursday, so I'm available anytime on Thursday for any help that you need, any questions that you have. Okay, having said that, looks like a bunch of people while I was giving the warm-up have shown up. And so good to see everybody on this fine Monday morning. Let's move on to perturbation theory. And let me stop sharing Canvas with you and move over to perturbation theory. And so we'll share that instead. And the first question might be, well, what do you need it for? Okay, and that's a good question. Why do you need it? And, we've done a bunch of problems this semester. Let me minimize that so it's out of my way. We're going to predominantly focus on the infinite square well, the very first problem we did back the second week of class. And I'll review that here in a second because it's been a while for us. But what if I have some kind of potential well, square well being the absolute simplest, and there's some little problem with it. It's not a perfectly symmetric well. There's some sort of bump, as I'm showing right here. Okay, what do you have to account for that? And I think about that as being one possibility. What if maybe I cut the corners a little bit? That might be another thing I might do to an infinite square well to take it away from the ideal model. The ideal model has got a great value and that we could solve it, right? And I think there's two solutions. Approximate solutions, and that's what perturbation theory is all about. And everybody here has taken Campbell's class on numerical methods, and so obviously you can do some sort of numerical solutions to these problems as well if there is some little kink in what would otherwise be an ideal differential equation that we have to solve. And so I want to remind you a little bit about the infinite square well. That was Schrodinger's time independent wave equation, sometimes called the energy eigenvalue problem. okay? And we're going to rewrite that, okay? All of this stuff, that's this and this, we've been referring to as the Hamiltonian operator. And now I'm going to superscript it with a 0, okay? The eigenvalue to that time-independent Schrodinger's wave equation, the energy eigenvalue problem, we're also going to subscript with a 0. And of course, the wave functions, the eigenfunctions now, we've kind of learned to call it that, are also going to be subscripted with the 0. That's the unperturbed potential. That's without this bump right here, without any variation. And of course, these wave functions in this, what I'll call the 0th state, are orthogonal, just like they've always been. Now, I want to make one point on these superscripts all the way through. They're not exponents, they're not powers. I've just often have an N. All right, I got an unstable internet connection, and so hopefully I'm talking again and you're hearing it. I have an N already in the subscript for the eigenvalue and the eigenfunctions. So the subscript location is taken. The decision was made notationally by somebody other than me, obviously, to put the various orders of the correction that result from our approximate solutions up in the superscript position. Okay, and so just so we're clear about what I'm calling these guys, back in chapter, I guess chapter 2 is when we did this. This would have been the Hamiltonian operator in H on psi is equal to E on psi. And all we're saying now is that's the 0th order. That's the 0th order wave function right here, and that's the 0th order energy. And of course, we've came to find that these wave functions and these eigenfunctions associated with were quantized, okay, because we actually solved this differential equation. We assumed a sine cosine solution. We ruled out, based on what happens at the boundaries, the cosine solution. Cosine of 0 is not 0 like I needed it to be, and I needed the wave function to be 0 at the boundaries, and so that left me with the sine solution only. The differential equation told me what this k had to be, and I guess we decided that Ka out at this boundary had to be an integer multiple of pi, because the wave function had to go to 0 out here as well. And so that gave me a clue as to energy, okay, because you see K had energy in it. And so that told me that that's my energy eigenvalue. And that's how we solved that problem back in chapter 2, okay? And the wave function then had that value of K right there. Where am I? Nope, I'm sorry, I had this value of K, check the wrong box here, had that value of K, and the normalization constant, square root of 2 over A right here. Well, we got it by normalizing the thing, just all the attributes we said before. Everything on this slide right now, back from chapter 2, would be superscripted with a 0, right? With a 0. The Hamiltonian would be with a 0, okay, with a 0. And that's all we're saying. So that was the basic problem with the perfect potential that we could solve exactly like we wanted. Okay, so that's my notation and a little bit of review, because we're going to be needing what the wave function is and what the energies are for the infinite square well. The problems that we're going to show on perturbation theory all perturbate the infinite square well problem. So a good chance for a review. Remember, n pi x over a is what you have in here. It's only a sign normalization constant. And there's my energy eigenvalue, h bar squared, n squared, pi squared over 2. I'm going to subscript the mass with the mass of an electron here today, because we're going to have an index m in a little bit, and times the width of the well, a. Okay, a little bit of review on that. Oops, went too far. And so now, how do I correct the Hamiltonian? And you're going to see me with these 3 equations over and over again. The point is, this little guy right here is the bump. That's the perturbation in the Hamiltonian. In this case, it's only in the potential. And I think every time I've ever seen a perturbation theory problem where the Hamiltonian gets a correction, it's only in the potential part. I mean, how do you change the momentum function? I mean, I just don't know how you do it. Doesn't mean it doesn't exist, just mean I don't know how you do it. And we're going to have a little multiplier right here. We're going to assume this is a small number, this lambda for now, okay? But eventually, once we make use of it, we'll just decide lambda is 1, and hopefully you'll see why I do that here in a second. So there's your basic, in the case of an infinite square well, just the momentum operator squared, right? Minus h bar squared over 2m. That's what that is. H bar minus h bar squared over 2m. And somehow I've got this little bump. And I'll show you a couple examples of how we can write that functionally. I don't know how I'd model a bump. I guess it's kind of part of a parabola, maybe. I don't know what I'd do. Okay, so that's how we're going to modify the Hamiltonian in Schrodinger's wave equation. We also have to modify the wave function, the eigenfunction, psi. And so there's the basic one for the clean problem that we did back in chapter 2. And then we're going to have that same little lambda that is just some kind of multiplication scaling factor. And then this will be what we'll call the first order correction. We'll call this the second order correction. And, depending on how accurate your approximation needs to be, you could continue on with more and more corrections. Okay. It just depends on what you need for a particular problem you're trying to approximate. Because remember, these are all approximate solutions. None of them are exact. They might only be good to 2 or 3 decimal places, whereas the original problem might have only been good to an order of magnitude. Okay, so that's the deal. We do the same thing with the energy eigenvalue. This is the energy eigenvalue solution I just showed you on the previous slide. Okay, we're going to correct it with a first order correction, and then a lambda squared and a second order correction. And so you always square the lambda just because a number that's small gets squared, it gets an even smaller term. These higher order terms, as you add them on, they become less and less important because they become smaller and smaller in magnitude of correction. It's kind of a series approximation that we're doing here. In fact, it's not even kind of, it is a series approximation. Okay, so if you take these things and you put them all into the energy eigenvalue problem, the time independent Schrodinger wave equation, okay, this guy goes right, gets replaced by that. The wave functions, the eigenfunctions come in 2 places, and energy comes right in there. And you can see that you got a bunch of things multiplied together, right? Because I have to multiply, oh, that looks terrible. I have to multiply that by each of those guys. I have to distribute these terms out. And of course, it's an infinite series. Same thing here. I got to take my energy and multiply it by each of those things, take the next energy correction, multiply it by all those things. And if you start expanding these things out, you get an awful lot of terms. And the only question, I guess, is, well, how many do you need to keep in order that your approximation should be accurate enough? Now, I will say this, for perturbation theory, and for us, we're only going to determine how to find the first order correction to the energy eigenvalue and the second order correction. We're going to ignore anything out here. We're just going to make that go away. And in terms of the eigenfunction, we're only going to determine the first order correction, and we're going to ignore anything higher than that. We'll just assume they're so insignificant, and quite frankly, they're complicated enough to get to get 2 to 3 of these that it's just not worth our time. But if you ever needed to, for any reason, you could do it. You'll see the pattern, and you could see what the next one would probably be, and be able to figure these all out. I will say this has more applicability if you're ever doing a model of some sort and you need to correct the model. A model can be corrected. A perturbation correction to any model is possible. We're just doing it for the specific case of Schrodinger's wave equation as the model for quantum mechanical systems. All right. Well, I said we have to do some multiplication, and so let's kind of do it. And remember, I said this is our Hamiltonian becomes minus h bar squared over 2m, the normal Hamiltonian, okay, and plus some little bump, some little correction we're going to do. And then the wave function gets all these extra terms, okay, not a power here. These guys aren't power. That doesn't mean psi 0, which is just 1 because you've raised it to the 0 power. Similarly, this doesn't mean psi squared here. It's just a way of indexing. I mean, I could have put the 2 down here, and we could have put the 1 down here. We could have put the 0 down there, and then you wouldn't have been tempted to take a power here. It's just the notation people have adapted. Same thing with the energies, not squared here. It's just the second order correction to energy, or the first order correction to energy. Anyway, it seems to me I got to take this and multiply it by that guy. And then I got it, so right there, kind of keep some of my bookkeeping. This guy right here multiplied by that guy. I guess we did that. Those are those two. And then I took a different tack because I'm just trying to keep track of these. I went that guy on that, which I think is that one. Yes, it is. And then I went that guy on that. And notice that's a lambda squared, isn't it? Okay, so up, nope. I wrote it right here. So that's that guy. It is a lambda squared. And then it's H prime, the little bump, times the first order correction. And then I got that guy on that guy, which is also a lambda squared. I think the next thing I would multiply out would be a lambda cubed. And I'm not going to do any of those. Okay, just done with it. I've stopped after. I think I've found all the possible ways to get lambda to the first power and lambda to the second power from the left side of the of Schrodinger's time-independent wave equation. Okay, got to do the same thing over on the other side where I take the eigenvalues times the wave function. Okay, and so I went that guy times that guy. All right, and I think that's the first one. And then I went that times that. Yep, I got it in that order. That got me a lambda to the first power. The other lambda to the first power is this thing times that thing. Okay, that got me a lambda to the first power. And then again, I was looking for all the lambda squared things because lambda is squared. Okay, lambda is squared. It is a I guess a power series where the coefficients are either my wave functions or my energy eigenvalues. This is actually a squared lambda. But in a second, I'm going to make lambda be equal to 1, and so it's just not going to matter. Okay? Any event, let's see, I got all the lambda to the first powers. Then I went for lambda to the second power, so that meant that times that times that, and that times that, and I wrote those guys out. And I think any other combination of distributing these series would result in a lambda cubed function, and I'm not doing those. I'm done. We're not going that high. Okay. And so I kind of lumped things together and factored out the lambda. And yeah, you're probably catching on. I color coded. Red is anything that was lambda to the first power. Blue is anything that was lambda squared. And in any power series, it is legitimate to say you have to equate coefficients of like powers in an equation. Okay, coefficients of like powers must be equal. And, I asked, everybody looks at me like, well, really? And the answer is yeah. If I have A plus BX plus CX squared is all equal to 5 plus 3x plus 7x squared. And I asked you, well, what's B, for example? I think everybody would tell me B is equal to 3, and you'd be right. It has to be, right? B has to be equal to 3, and A has to be equal to 5, and C has to be equal to 7, because you have equated the coefficients of like powers of, in that case, X. Okay, well, of course, that's lambda 0. And that's multiplied by lambda raised to the 0 power. Anything to the 0 power is just 1. The lambda is actually to the 0th power, to the first power, to the second power. And so this is, I guess, the 0th order, which is just the equation we saw back in chapter 2, the one that I took you on a review of. If I look at the red equation, though, that must mean that this has to be equal to that. And that's referred to as the first order correction equation. And we'll figure out what that is here in just a second. And I've got an unstable internet connection, so I'll kind of slow down a little bit. And then here in the blue, okay, that's the second order. That's anything that was multiplied by lambda squared. Those two coefficients also have to be equal, and they're referred to as the second order correction. Okay, and so, or the second order equation. And so the game here in perturbation theory is you got to either have to know, because we've already solved the problem, what the eigenfunctions are for the unperturbed potential and the unperturbed Hamiltonian, and you have to know what the unperturbed energy eigenvalues are because they start this, and then I can, from these two equations, I guess get the first order correction is right there to the energy, and then I guess it's also right here. And then I could get first order corrections to the wave function right there and right there. And we'll see how these things mathematically reveal themselves here in just a second. But that's the game. And then you come on back up, and once you know what your perturbation is, you can figure out what your corrections are here and here. And there's no longer a requirement for lambda to have any particular value in these series solutions. Okay, and so we're just going to make it 1. And that's the argument. It can be any value. Let's make it 1. There's no reason, it has no units. There's no reason to think it's anything other than that. And so forevermore, we've only used lambda as a mathematical device to get like correction terms in our power series to be equivalent to each other. Once we've achieved that, there's no longer any need for the lambda or the lambda squared. We'll just get rid of it. And never again will anything be to the first power or be squared in any of these problems. All right, so let's talk about first order theory. Okay, so we're basically looking at the perturbation in the Hamiltonian, and we're trying to get initially the first order energy eigenvalue correction to the normal one. Okay, remember again, that's just h bar squared, pi squared, n squared, since it's indexed to n, over 2 mass of the electron that's in the infinite square well times the width of the well squared, right? That's what that is. We're going to try to find the first order correction to that. And so here's the deal. I remember that was the red equation, the first order equation, which was like coefficients of lambda to the first power. I equated that. The first thing I did is multiplied by the 0th order eigenfunction, and remember that guy is just square root of 2 over a times the sine of, I guess I'll just write kx, where we knew that k was n pi over a, okay, and so that's what I'm pre-multiplying each of these by, and I should really be more specific, that's n pi over a, right? Because it's any value n would be that. Okay, so that's what I'm pre-multiplying by. And then I use our new notation from chapter 3 to do the integral. And don't forget, this means I'm integrating, I guess, psi n0 complex with whichever part of the operator I have, either h0 or h prime, psi dx. That's what I mean by this guy. That would be h0 for the first one. And then, of course, second one would be h prime, which has whatever the perturbation is. And then on the other side, well, hopefully you can see what these two become. The energy eigenvalue is just a constant, so it comes outside the integral, right? And that's why I wrote this right below it. And again, this energy right here, the first order energy correction, comes right out outside the integral. And what's left, interesting enough, on this particular one is the Dirac delta of something in itself, so that's just equal to 1, right? Okay, so that term kind of takes care of itself, and you can see that's what I'm going to be able to solve for that's how I'll be able to solve for the first order energy correction. Now, I want to take a look at this. So out of the 4 terms that I had originally here, when I do, it's hopefully a very logical process. If you would expect to do anything else at this point in the course, I think. I want to take a look at the first of the 4 terms. The last one, you can see that's going to give us the first order correction to energy. The first one here, though, I can exploit the fact that the Hamiltonian is a Hermitian operator. Right? If the Hamiltonian is a Hermitian operator, and it is, it gives an eigenvalue that's real, blah, 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 all the things that we've done to prove that something's Hermitian, that means I could put it right there, which I did, interesting enough. And then I can, employ the 0th order equation. The Hamiltonian operating on that guy is just E0 times n. And you see why that was useful. I have no idea what the Hamiltonian, the 0th order, the regular minus h bar squared over 2m, does to the first correction. but I do know exactly what it does to the standard, the regular, the unperturbed wave function. I know exactly what that does. So the fact that this was a Hermitian operator was very handy here, right? Because I now know the answer. It's that. And of course, that's a constant, which could come right outside the integral, and that's what I did right here. Okay, I want you to notice this term right here, okay, which is written incorrectly now that I look at it. This should be N0. This should be N0, right? That's what it should be. It's actually correct when I go to put it right back in here, because now I'm taking this guy with that correction, N0. I just wrote it as E0, which it would have been, I guess, back in chapter 2, but it's not consistent with the notation. So when I took that term, exploited the Hermitian nature, knew what to do with the Hamiltonian on the regular wave function, okay, I put that right in there. And what you should notice is it's exactly the same as that term right there. So those two cancel. That guy and that guy, once you've done this correction here, cancel. Boom. And if I solve then for the first order energy correction, it must be what's left. And that's an interesting result. It came from, let's see, this term, which was that term, which came to that term, which came to that term. What that is the expectation value of the perturbation, but in the unperturbed state, right? The zero state. That's the first order correction to the energy eigenvalue. Okay, let's see what that means. Let's do an example, maybe even two. Okay, actually, I guess I got two set up here. Here's the infinite square well, but across the bottom, we've bumped up all the way across from x equals 0 to x equal a. We've got a perturbation. We've just bumped it up by some amount v0. Okay, so instead of the infinite well starting with a potential energy of 0, it starts with some value v0, not 0 volts or electron volts, 5 electron volts, for example. Okay, well, what's the first order correction then? It says do this, find the expectation value of the perturbation in the unperturbed state. Now, that's a pretty easy integral to do because this guy is just a constant, all right? And so when I do that, the constant just comes out front. Those are orthogonal. It says the first order correction is just that extra distance. That should make perfect sense, I hope, because this was a pretty trivial example. Okay, well, let's try something a little more complicated just to see what a bump like this is. Still a square bump going across just half of the potential well. It's up to some value v0, so it's not quite as trivial a problem as this. We write perturbations like that. It's multi-valued, so it has a value v0 in the range x from 0 to a over 2, and then it's 0 from a over 2 up to a, right in there. Okay, now that's my perturbation. Well, that one's a little harder to do, right? You actually, no kidding, have to do an integral. When you had a constant, you were just able to just kind of say that you know what the value of the integral was. When you bring the constant outside the integral, it's a normalized wave function, so it's just 1. But now I no kidding have to do an integral. Actually, I have to do 2 integrals, don't I? Because the potential right here is I factored out the v0. I factored out, where did 2 over a come from? Well, remember, psi 0 here for any n is the square root of 2 over a, okay, times the sine of k times x, n times pi times x over a. Since that's what 0 is, when I squared it, right, it became squared, and the 2 over a became squared. It came out front. And the potential is still just a constant over that range, but notice what my limits of integration are, 0 to a over 2, which is hopefully what you'd expect. But then I also have to go from a over 2 to a, and since the potential is 0 right now, there, the integrand everywhere is 0 times, of course, sine squared and pi over ax, but 0 times anything still is 0, and so this guy goes to 0, right? And so that's the answer for the second part of this integral. But we still have to do this. And so let's see, from 0 to a over 2, I'll be honest with you, I did this in Wolfram Alpha, but you can, we've done what's the integral of sine squared dx multiple times during this course. It might not surprise you that it's the upper limit of integration divided by 2. Okay, and it is this case. You can check it, but I did that in Wolfram Alpha. And then I still got the constants out front. And let's see, the A's cancel. 2 over 4 becomes 1/2. Looks like it's V0 over 2 would be the first order correction to the energy eigenvalue. So, let's be complete here, I guess. The energy eigenvalue for the nth state, I guess, over here on the first example we did would be, let's see if I can write it out without messing it up, h bar squared pi squared n squared over 2 mass of the electron times a squared. And in this case, where I bumped it up, I would add on the correction right here, V0, the first order correction, okay? And so that's what I would add up for this case. Over here, I would do exactly the same thing. I'll write it up here. The energy eigenvalue for the nth state with this perturbation right here would be, I'll write it again for you, h bar squared pi squared n squared over 2 mass of an electron times a squared. But in this case, with this perturbation, it'd be plus V0 over 2, right, would be the first order correction. All right, there's going to be another correction we're going to look at because this is what we called E1N. This is E and a 0n, I guess, 0n, and we added those two together. We're going to be working, and we may not get to it today. We'll certainly finish it up on Wednesday. We'll find the next order correction, the E2 correction. But just looking at the clock, I don't think I'm going to get to that today. By the way, the tutorial has us do neither of these two, okay? Let's pretend this is the x-axis right here, just so I can redraw what the tutorial has us do. It has the perturbation being a linear function right here. So h prime is equal to some slope, call it epsilon, times x, okay? And so if you were trying to find the first order correction to the energy eigenvalue, this guy right here, in that case, it's not that hard a problem, I guess. You do exactly what I did here. In place of the V0, though, I guess you would put a constant times x. So I think in that case, the first order correction to energy would be, let's see, you'd still have the 2 over a from taking the normalization constant. So it'd be 2 over a. And then you'd have the integral. Now, here, the perturbation is over the entire range, so you don't have it being multi-valued like you had in this little step here. You just integrate from 0 to a, and then I guess you'd have sine squared of n pi x over a, but then you'd have to put in your perturbation. Now, epsilon's a constant, so it can come outside the integral, and you'd have to bring in the x right there. It actually goes in between the two signs, doesn't it? It's really sine complex conjugate, but that's all real, so its complex conjugate is itself. Then it's x, then it's the other sign, but you can see that they commute. It doesn't matter which order I write them, all times dx. And that's how you get that first order correction. Yeah, it's a difficult integral, but Wolfram Alpha does that one quite nicely. And so that's how I did it. And you should find that the answer that you get for that makes some degree of sense to you. It might, if you look, since it's linear, you might expect it to be the value of the perturbation kind of at the midpoint, which is often what an average over a midpoint does. It's been said that this first order energy equation correction, first order eigenvalue energy correction equation, I guess is what I really want to say, is the most commonly used in quantum mechanics, because we can very often approximate some potential with one of the problems we've already solved. And then the question might be, well, how do we have to vary on that thing we've already solved to actually solve the system we've got? And the first order energy correction does a very nice job of taking something that is generally wrong and giving it a reasonable correction that gets you fairly accurate. Okay, even the results you'll get right there. Okay, so I think that's it for first order energy corrections. And that's a little bit of taste of perturbation theory. Let's answer one more question and then call it a day. What's the eigenfunction now? Okay, so we've already got this guy. And remember, lambda 1, lambda squared 1 once we got it. So we put that together with that. And we figured out a way to get that. You go psi n0 h bar psi n0, and that's how we get that thing. Okay, good. How do we get this now? How do we get that thing? Okay, well, I guess what I did was I took this red equation again, the first order equation, and I brought this guy to the other side of the equation because you'll notice it has the first order correction to the eigenfunction right there. And then I brought this to the other side over here because they're both multiplied by the original, okay? And then I'm gonna make a proposition that this first order correction to the eigenfunction is just gonna be a coefficient times the 0th order, and I'm indexing m here instead of n, the regular ones that we studied back in chapter 2, okay, with some coefficient in front of it that changes the amplitude of each one, okay, in a series. And it turns out that there's a good mathematical reason why in this series the actual value right here is not a member of that series. You'll see in a second that would require us to be dividing by 0, and that's not allowed. And so that would be a whole nother perturbation theory. That's called degenerate perturbation theory when those two guys are allowed, and that's something we're just not going to do this semester. But in any event, that's my assumed solution that's going to go right in there, okay? And so that's what happened. These coefficients, they almost look like Fourier coefficients, don't they? I'm not going to call them that, but this is it's to the nth eigenfunction. There's a whole series of these coefficients that we've indexed with m because that's what we're doing, and that guy is right there. Okay, let's see. If I have this acting on that guy right there, much like in the energy correction, we know what the answer to that is. That's just the energy eigenvalue times that same function. Kind of cool, I guess, that we can determine that that first order correction is going to be a series of the 0th order wave functions, because that allows me to do that, because that's just a constant now, I guess. And the other side just stays as it is. All right. I get, and that's, if you're not following what I just did right there, I just made use of the 0th order guy. And then I guess, like we often do, because that's what we did before, if I pre-multiply by, in this case, it would be psi, I'm up to a new index here, I'm up to L0 complex conjugate, and then I integrated, that's why I wrote it in those brackets, and I do that for each term here. That guy went to that one, and this guy went to that one. See, I pre-multiplied by the same thing each time, okay? That would let me simplify my equation, okay? Let's see. If m isn't going to be equal to n, then that's equivalent to saying L and N aren't equal here, I guess, right? Because if the only way this thing could have any value is if L is equal to M, right? Otherwise, this term right here goes to 0, and it's kind of a trivial example. So the only non-zero value of this integral right here is when L is equal to M, because this, remember, is the Kronecker delta still, L, M, okay? Since that's the Kronecker delta, L has to be equal to M for this to not to have a value. And if L is equal to M and N can't be equal for reasons we'll see here in a second, well, L and N can't be equal either. Okay. And so I guess that collapses this sum down a little bit to me just summing over, let's see, this becomes, M becomes L to make that work. N stays as N. This guy becomes L, and I used to have a sum, but now I don't anymore. I've just got the one term in the sum that isn't 0. And again, now instead of M not being equal to N, L can't be equal to N. All right. And now let's look what happens on the other side over here. All right. On the other side, I guess nothing changed here. Nothing changed here, but unless L, which had to be M from over here, unless those two are equal, which we said they can't be, that term has to be equal to 0. It's kind of about a 3 or 4 step logic sequence there, but I think you have to agree everything I said is true. That pre-multiplication step by this was handy because only L and M being equal causes this term not to be 0. I make L and M be equal to each other. Well, L's, and we've already had the conclusion that M's not going to be equal to N. You'll see why here in just one more step. It kind of comes in at the end, oddly enough, but it's true. Okay, that means this is true. All right, and so now I can solve for that guy. Now I can solve for that guy. And I just brought this to the other side of the equation. There was still a negative sign right there. And now hopefully, and I've re-indexed. I went back from L to M because that's how we started. You can see why M and N can't be the same here. If M and N were the same, I'd be divided by 0, not allowed. Okay, so pretty clearly M and N can't be the same, and this is the step that proves it. You can make a mathematical argument why you wouldn't allow them back then or why you don't need them back then to have a complete solution. But right here, if these guys were the same, a particular state, I guess, would have the same energy eigenvalue. It's just not allowed, okay? And in the case of a degeneracy, I would also have 0 there because if M state has the same value as N state, that would also be equal to 0. So M can't be equal to N, and even if they are two different things, you can't have the same energy right there, which is called degenerate eigenvalues, not part of this theory. Right? In any event, it's conventional to drop that negative sign, reverse the order right here, and those are the coefficients. Those are the coefficients right here that are in my original assumed solution. Okay, so kind of the process is you got to figure out these coefficients, okay, and then you multiply them. Well, look at that, that actually did exactly what I wanted. You have to multiply them by the eigenfunctions of the standard chapter 2 Schrodinger wave equation for an infinite square well. Okay, and that is the first order correction to the wave functions. Okay, so I guess the game here is all about finding that. Okay, because you know what these guys are, right? Those two things in the denominator for an infinite square well case are exactly what we said. E sub n, and I'll write it one more time, is equal to h bar squared, pi squared, let's see, n squared or m squared, depending on whether or not you're getting this one or that one, okay, divided by 2 mass of an electron times a squared. And hopefully it's clear right now why for the mass of an electron, I'm going to subscript it with E, because in the notation, I have an M that's not the mass of an electron right here and right here and right here, okay? So to keep that clear, I'm going to not have that. We also know these guys from back in chapter 2. I already wrote them up once. The whole game is figuring out what those are. And before we quit for the day, I just want you to think about what that's going to be for the problem I talked about with this perturbation, which is an increasing ramp on the infinite square well. And let's think about what this term's going to look like. Okay. Notice I've got M here and I've got N here. Okay, and so let's just take a second and write out that thing because everything else is just algebra, okay, or things you already know. This is the deal right here in finding this first order correction to the wave function. Okay, so let's see. What is that? That was psi m 0. Okay, it was h bar. Very similar to the energy correction, right? Except now it's psi n right there, 0. And so that thing looks like, well, it's the same normalization constant, 2 over a, square root of 2 over a from both of these two things. I've got to integrate from 0 to a. Now, be careful here. Sine of m pi x over a, okay? And then that thing is multiplied by that epsilon x, because that's my perturbation, right there. And then this has to be multiplied by sine of n pi x over a. And then m and n are not equal here, as we said over and over. M and n can't be equal. Integrated dx. That's what that thing is, okay, that gets you your first order correction to the energy, I'm sorry, to the wave function, okay, the first order correction to the wave function. When you divide through by the energy eigenvalues difference squared, and you multiply by psi itself for a particular order, it gets a little complicated. But my point here, I guess, is this important piece I couldn't get Wolfram Alpha to do without running out of time. And so when you look at the tutorial, there is a couple hints to use some trig identities and then some tabulated integrals to do it. I did find that once I put in the trig identity, which simplifies this, and I think the trig identity of concern here is that when you have two signs multiplied together, sine A, sine B, the trig identity is that's equal to 1/2 the cosine of the difference of the two angles, cosine A minus B, and minus, and there's the 1/2's distributed, minus cosine of the sum of the two, A plus B. And you can see that this guy right here might be A, and this guy right here might be B. And so I've got sine A, sine B, and I can make it two cosine integrals out of this single sine integral. And I was able to get Wolfram Alpha to individually do the two integrals by themselves. And then I had to do the combination of the two as I put it all back together. And so that's just a little help on the calculus of this problem, okay? And so what have we done so far? And the hints I've given, I think we've talked about, okay, so I've got some sort of perturbation, and we've looked at 3 examples of perturbation to the infinite square well problem, where you just bump up the bottom of the well, just some amount V0, where you put a little notch on half of the well, or the problem on the tutorial where you put a little ramp across the bottom of the well to change it from the ideal solution. We've shown how to get the first order correction to the energy eigenvalue with a pretty simple equation. It winds up essentially just being an expectation value kind of problem, which could be a complicated integral, could be not, okay? And then we talked about how to get the first order correction to the wave function. That's a little more complicated, as we showed here, okay? Because the big deal is getting this thing. But once you've got that, you just divide through by the difference in there, which is a little tedious, but you can do it. And then you multiply by the 0th order wave functions. And so you could have for a particular n, like n equals 1, you could have the n equals 1 wave function, and then 3 or 4, however many you want to carry out, terms that are the correction to first order. Okay, we won't ever do a second order correction to the wave function, but come Wednesday, we'll talk real quickly about the second order correction to the energy eigenvalue, and then we'll call it a semester. All right, that's enough. I'm going to stop sharing this with you, and we'll kind of call it a day here. Any questions real quick before we log out? All right, I see people going on to the rest of their day. You all have a great day. I will have office hours available this afternoon for anybody who wants to talk, and we'll see you on Wednesday. Have a great day.